All right, determining the length of an arc. Now, I've actually already addressed this. I talked a little bit about this in, I think it was the second video, where we talked about converting between radians and degrees, because there we defined this arc, this thing that was a partial circle. I just did a terrible circle there. I'm going to try a better one here. That's a little bit better. We took a partial circle, maybe from here to about there. That's an arc, okay? So part of the way around. Now I could put that anywhere, but I'm putting it in this starting in standard position just because we want to do that as much as possible. If we're starting in standard position, then we know we're all starting on the same footing and there's less confusion. So what we do with this arc, though, first of all, is we give it a name. We're going to call it S. The length of the arc is S. And in that second video, we also defined or derived a formula, S equals R theta, so that we know we can find the length of this arc if we know the angle theta, which is, let's see, I'll try to draw that in here. It's the angle swept out by the initial ray, or between the initial ray and the terminal ray, right? If we know that angle, if we know what this angle is here, we can call that theta. I'm going to make this a little bit smaller. Oh, it's as small as it's going to get. I wanted a really thin pen there. We call that angle theta. Then if we know theta, and if we know r, the radius of the circle, then we can determine s. It's really just a matter of plugging in some values. So let's try one. Find the length of an arc subtended by an angle of 5 pi over 6. The word subtended means swept out, or the length of an arc cut off by an angle. So first of all, if we want to picture what this is, what the situation is here, we need to figure out what an angle of 5 pi over 6 is. And we're going to be doing a lot of this throughout the term, but for right now, let's just kind of use this as an example. We have 0 radians here. I know that I'm in radians, by the way, because my angle has a pi in it. Now, I could theoretically use pi in an angle that was in degrees. For example, I could say 2/3 pi degrees, but it's unlikely. It's highly unlikely. If it's got pi in it, it's almost always in almost always in radians. And if it is in degrees, it has to have the degree symbol. So if you don't see the degree symbol and there's a pi, it's definitely in radians. So I know I'm in radians here. There's 0 radians. Here's pi radians. And as we discussed earlier, going all the way around gives you 2 pi radians, right? 0 radians and 2 pi radians are coterminal angles. All right, so I want to find the length of an arc subtended by an angle of 5 pi over 6. So what is 5 pi over 6? Here's how I think about this. If I want 5/6 of pi, that's what this is, 5/6 of pi, then I try to figure out what is 6/6 of pi. Well, that's 6 pi over 6. That's 6/6 of pi. All right, that's just pi. And I use 6/6 because the denominator of this fraction is 6. So I want to compare this fraction to this fraction, or pi. So find pi, that's 180 degrees. That's equivalent to 180 degrees if I convert it to degrees. So it's over here at 180 degrees, or pi. And I want to take 1/6 of pi less than that. So I'm going to go back a little bit. Remember from our diagram, we didn't really spend a lot of time on this, but there's 45 degrees back from pi, from 180 degrees. That's a little too far, right? 45 degrees is too much. So I want to come back to about here. That's 30 degrees less than pi. So this is approximately 5 pi over 6. And for my purposes, that's close enough. I just kind of want to visualize it. You don't necessarily need to do that, but if you did want to visualize it, that's maybe how you could do that. Now my job here is to figure out the arc subtended or cut off by an angle of 5 pi over 6, and I don't have an arc yet. So what I really want to do now is draw a circle around, starting at 0 and going around. And I could draw the whole circle if I want. What I really need is this part right here. I'm going to use this lurid pink color. It stands out so well. I want the length of this arc. So I'm going to use my formula. S, that's the length of the arc. That's my S. S equals R theta. So S here equals R times 5 pi over 6. What's missing is the radius of the circle. I haven't told you what that is. So let me add that to the problem. You would need that in any case. So find the length of the arc subtended by an angle of 5 pi over 6 in a circle of radius 2. Well, I've substituted 5 pi over 6 for theta. I'm now also going to substitute 2, where's my pen? 2 for r, the radius. I'm told the radius is 2 millimeters. Right? So when I do this arithmetic, I simplify this, I'm going to get S equals 5 pi over 3. I can leave it like that. And S is a length, right? It's a curved length, but it's a length. And so it's going to have to match the units that I have here. So the answer is 5 pi over 3 millimeters. The length of this arc right here, if the circle has a radius of 2 millimeters, and this angle is 5 pi over 6, then the length of this pink line here, this pink curve, is 5 pi over 3 millimeters. Now, can you convert that to a decimal and figure out like approximately, realistically, how big it is? Sure. But you know how to do that. I mean, you can plug this number into a calculator and figure out what the decimal equivalent is, right? But it's going to be an approximation. So I would like to invite you to please leave that as an exact value, at least for now. There will be applications where it makes sense to convert that to a decimal. But we're not working on an application here. We are literally just plugging numbers into a formula. So let's not mess with changing anything. Besides that, it's an extra step. If you plug this into your calculator wrong, you're going to get the wrong answer, even if this is the right answer. Okay? So that's really all there is to it for this video. There is one caveat, one thing to look out for. If I ask you to find the length of an find the length of an arc, find S for, let's say, theta equals 30 degrees. If the circle, let's call this radius, I'm just kind of using some shorthand here. I'll even use the same radius here, okay? It's very tempting to say, well, S equals R theta. So that means that S has to equal the radius, which is 2, times 30 degrees. We cannot do this because, I'm going to highlighter here, this is not in radians, right? This is not in radians. You first have to convert it to radians, which is 30 degrees times pi over 180 degrees, which is, let's see, degrees and zeros cancel. 3 goes into 18 6 times, so I get pi over 6. This is what you have to plug in to the formula. So be careful about that. Other than that, that's enough for this video, and we're going to talk in the next one about finding the area of a sector of a circle. It's a related concept. For example, the piece that I have highlighted here, right, and colored in, shaded in here, those are sectors of circles. So that's our next video.